All right, everybody, I think I've got 10 o'clock here, and so I know there's some people still straggling in, but I'm gonna go ahead and try to get started right as usual. I hope you guys are doing well as we start a new week. I'm just gonna make a few announcements and then we're gonna hit the math a little bit today. We're in chapter 2. But before I get to that, just a couple of comments. First of all, about homework, we've now turned in 3 assignments. Boy, my grader is fast. I have a new grader this semester. I can't believe it. I woke up this morning, he's already got the papers graded from last night. So I don't know what time he gets up. Anyway, so he's really fast at grading, at least so far. I'm hoping that'll keep up because it's nice to get the feedback. I just want you to understand how those papers are being graded. Every assignment is out of 20 points, and you'll find those points broken into 2 parts. Part of it is you're just going to get some points just for turning it in. Everything could be wrong, right? But if you at least try to solve the problems or whatever and turn them in, you're going to get some points. And usually that might vary a little bit from one assignment to the next, but I would say roughly on average, it might be about 6 points of the assignment, 5 or 6 points, just for turning in a complete assignment. Obviously, if you turn in half the assignment, you're only going to get half of however many points that is for that assignment. The remainder of the 20 points, however many are left over, my grader is actually checking some details of your work, specifically on problems that he has chosen. I noticed on the last assignment, I think he chose both of the problems that we had done in class, which is great for you guys because probably you're getting it right if you were here taking notes on it in class. But you'll get some amount out of the remainder of, let's just say you happen to miss 2 points somewhere. So on the top of your paper, you should see something like this. This would be like, here's the points that you got on the stuff that was carefully graded. And then here are the rest of the points for just turning it in. And then, you just add those up and that gives you a total out of 20. So that's kind of how these papers are graded. Now, keep in mind that not every problem is being graded. And so you could get a 20 out of 20 on an assignment. That doesn't necessarily mean that there's nothing for you to follow up with. I would recommend that you go to the Canvas page, and in the files section, there is a folder called Homework Solutions. And you notice over here, I've published the first 3 homework solutions. So you can pull these up as soon as you've turn them in, you can pull them up. And so maybe on some problem that wasn't actually graded, or maybe on a recommended problem, remember there's some recommended problems that will definitely not be graded. You might still want to just check your answers and check your work against this solution key. Definitely encourage you to do that. What I would not be so excited about having you do, and I already know that some people have been doing it, is going on to some other external site like Chegg or Slater, or there's these online forums and looking up your answers there. I can tell you right now, those people aren't that good at math. I have looked at the solutions that have been on Chegg for my own book, and half the time they use totally different notation. It's not what I'm teaching. It doesn't look right. My grader is going to flag it immediately, and you're not going to get any points for it. So I highly recommend that, if you're stuck on the homework, or you're trying to check your answers after the fact, use these solutions, which are solutions that I actually wrote up, and use my office hours and use your classmates and all that. That's the right way to do this, not trying to learn it off of some external site where half the time it's in a different notation and the other half of the time they're not getting it right anyway. So I've noticed that through the year. Anyway, so I just wanted to point that out, that's all there. The other thing is, if you get your paper back, I've already had a couple people do this, and this is totally okay. If you're not sure why you lost points, or you don't think it was fair that my grader took off points, remember that I am kind of the ultimate authority on it. So you can certainly bring your homework to me and say, hey, you took off 3 points, and all I did was make a little sign error or something like that, right? You can bring that to my attention. I can kind of do a separate evaluation of it, and I might give you some points back, or maybe I'll try to explain why I think he did what he did, right? So you can definitely check in with me about the grading on the homework as well as the solutions to the homework. And so I just wanted to encourage you to do that. Don't just turn in the homework and then forget about it forever. Right? There's actually some follow-up that would be helpful. Any questions about that? Or so good? Okay, and then let me just see a couple of other announcements. There's nothing due today. The assignment that you hopefully are going to be starting to work on soon is the one that will be due on Thursday. On Thursday, I'll take some questions on it. It's a pretty fast assignment. It's the first part of chapter 2. So they're going to ask you to add some matrices and to multiply some matrices and to write down some linear systems of equations. It's kind of the basics of chapter 2 on linear algebra. So that's what the next homework is for Thursday. You can come to my office hours today or Thursday or ask questions on Thursday in class about it. But that's coming up. The assignment following that one will be due. Well, I've currently said on Sunday. I might move it to Monday again. We'll see. I'll have to see how my weekend is looking. Great. Also, did everybody get a chance to watch that 7-minute video that I asked you to kind of added it to the assignment? I didn't really tell you what to do with that. If you didn't write up the notes, it's okay because there was a handout for that. So just so everybody's familiar, if you go back into the files section, there is a special handouts folder here. So under special handouts, there's a bunch of files, and I'll tell you whenever there's something here for you to look at. The special matrices handout is right here. So I'll open this up for a second just to show you. What you have here is basically the notes on that 7-minute video. Okay, so basically that's what it's about. Did anybody have any questions about that video? The idea of a symmetric matrix or a skew symmetric matrix. We also have upper and lower triangular matrices. These are all for square matrices, right? So you have to have the same number of rows and columns, right? So n by n size. If you have that, then you can make sense of these ideas. If the matrix is not square size, then of course we can't talk about it being symmetric or triangular or anything like that. But is this, or were there any questions about that? Yes, go ahead.
Those skew symmetric matrices, the main diagonal has to all be 0, right?
Right, so when you transpose a square matrix, this main diagonal, right, which is the numbers in the 1, 1 position, the 2, 2 position, the 3, 3 position, those numbers actually don't move, right? It's almost like there's like a pivot point along that main diagonal, which goes from the top left to the lower right corner. And so you're flipping the matrix. When you transpose the matrix, you're sort of flipping it along this main diagonal. And since the main diagonal does not move, and since the skew symmetric matrix has to be the negative of the, so when you transpose it, you're supposed to get the negative of the original matrix. Well, the only number that is the negative of itself is 0. That's the only number. When you take the negative of it, it stays the same. So these numbers on the main diagonal would have to be zeros for a skew symmetric matrix. Okay. As far as all of the other numbers go, when you transpose the matrix, obviously there's just sign changes. So whatever 3 numbers are above the main diagonal, right, would have to be negated in the corresponding positions below the main diagonal. Yes, Tom.
Can the upper numbers be negative and then the lower ones be positive?
Yeah, absolutely. These could be or it could be a mixture, right? All I'm saying here is that there's a sign change between the numbers in the upper triangle of the matrix and the numbers in the lower triangle of the matrix. Of course, none of that is true for the symmetric case, right? For the symmetric case, you do not have to have zeros on the main diagonal. And there's no sign changes required, but you just have to have, again, a mirror. There has to be sort of a mirror across this main diagonal. So the numbers above the main diagonal have to match up with the numbers that are below the main diagonal. Does this make any sense at all? Hopefully I'm making good sense. Okay, so those are the definitions of symmetric and skew symmetric. We are going to see these as examples that come up a fair amount. So if you want to know the definitions and kind of what the form is. The reason I wrote these examples over here was just to give you kind of what the form of those matrices is, so you can kind of recognize the shape and the style of how those matrices are filled out. Upper and lower triangular matrices, similar thing, you have to have a square matrix, but this time parts of these matrices must be completely zeros, right? So for upper triangular matrices, everything in the kind of the southwest corner of the matrix, the lower left corner, has to be zeros. Whereas for lower triangular matrices, it's the northeast part of the matrix in the upper right corner that has to be all zeros. Great, and then there's also the diagonal matrices, and there's a couple more things down here at the bottom. Again, I know you've watched the video, I won't dwell on this too long, but a diagonal matrix only can have numbers on the main diagonal. Right, and anywhere you see a letter, like an A or B, a C or a D or whatever, that could be zero also. But it has more latitude to be any other number as well. But for a diagonal matrix, you have a lot of zeros in that matrix, and those are very computationally friendly matrices to work with. I cheated a little bit here with number 6 because it's not necessarily for a square matrix, it's really for any matrix. If you have all zeros in the matrix, it's just called the zero matrix. And then this one down here, number 7, oh, this is an important one as well. The so-called identity matrix, I sub n, or sometimes it might just be written as I if we kind of don't care about the size so much. This is a diagonal matrix that happens to have ones on the main diagonal. And what I would have said in my video about that is that this matrix, when you multiply it by another matrix, it leaves it alone. It doesn't really issue. It's like multiplying by the number 1. Right? If you take 1 times x, you still have x, right? So this matrix times any other matrix just gives you that other matrix back again. It has no effect on it. So that's kind of an important one. We will definitely be seeing that from time to time also. Okay, so anyway, just wanted to go over the handout briefly with you. Are there any questions on that? Yeah, Eduardo?
Could it go the other way as well for like,
This way?
yeah,
That's a great question. That is absolutely a meaningless diagonal. So although it is fair to call it a diagonal, it doesn't really come up in linear algebra. So the diagonal, the main diagonal is really the only one we're going to care about, which goes from the top left corner to the lower right corner. Yeah, good question. Anything else for now? Okay, well, anyway, guys, the Canvas page is loaded up. There's lots of stuff here. If you go into the pages section, I've been starting to post these class lectures. So if you missed anything from last week or you just want to review it again, yeah, just go find my YouTube video on those lectures from last week. You can review anything you want. I'll just keep piling them on as we go through the next 3 or 4 months here through the semester. So. All right, well, let me just turn that off then for now. You can always ask more questions about that later. I have one other announcement, and then we're going to get back into this stuff we were doing last time. Tomorrow is the last day to drop this class without having some kind of a W on your transcript from the class or whatever, right? It's the last day to drop, but it is also the last day to add. So, well, I should say it's the last day to add without needing like 5 signatures from the administration and pay an extra fee and all that stuff. So if you want to have an easy add and you're not yet added to the class, you should be getting that done by tomorrow. Also, just because you're in Canvas, there are a couple people who have not used their add permits. That's why I'm bringing this up. Just because I added you in Canvas doesn't mean you're added to the class. Right? I did that just kind of to be nice, to let you kind of start working on the stuff before you were officially enrolled, but you're not actually on the roster just because you're in Canvas. And so you need to make sure, I would recommend for everybody to just double check that you're enrolled in this class. Most of you are. Anybody whose names I read off last week for attendance is already on my roster, but there's a couple people who I am still a little bit worried about. You being one of them. So anyway, that is it for my announcements. I think I'm going to come back over this way and like I've mentioned before, it's always a good idea to kind of review your notes on a Tuesday morning before you come in here after 5 days of not having 250B in front of you. But I'm helping you out a little bit here. I've got kind of where we left off on Thursday on the board. After spending most of Thursday just talking about like matrix operations and algebra, I want to bring it back this week to the subject of solving linear systems of equations, okay? And of course, we're going to use matrices to do that eventually, but I want to start having a little bit of a conversation about how to solve a linear system. So I got through, there was going to be 3 remarks, and I only got through about half of this list on Thursday, so I'm going to kind of pick this back up right now. This is in section 2.4 of the book, and it's called EROs and REFs. And the first remark, we mentioned this one last time, is that a linear system is always easy to solve by back substitution as long as it is in triangular form. And over here on the left, I reminded you, I did an example last week where I kind of made this system. The left side kind of looks shaped like a triangle. And I think we all figured out last week that, yeah, this is pretty easy to solve. We can first just write down what z is, which is 4, right? Then I can plug that value into the previous equation and solve for y, which I believe gave us 3. And then we can take the y and z values and plug them back into the first equation and solve for x. And I believe that came out to 11/2. So this is just solving by back substitution, okay? Great. Well, the problem is that most linear systems that we are going to face are not triangular to begin with. And so my second remark is going to help us deal with that. And that is that we will not gain anything or lose anything if we perform certain operations on our system. And there's 3 of them. These are called elementary row operations, or in other words, EROs. And we're going to have a lot of time this week practicing doing EROs. But let me write down the 3 elementary row operations that we can safely apply to a linear system without worrying about gaining or losing solutions. Okay, so the first one is we can permute 2 equations. We can permute 2 equations. And we are going to have some notations for this that I'm going to want you to be using when you're working on homework for this section. And I'm going to denote this as PIJ. PIJ. P, of course, stands for permute. Permute is just a fancy word for swap or interchange, right? And the 2 equations that we are interchanging when I use the notation PIJ would be the ith equation and the jth equation. Those are the 2 that I'm interchanging. So I think you guys would all agree, would you not, that if my linear system over there that I have written down on the far left, you don't need to write this down, I just wanted to show this to you. If I decided to swap 2 of the equations, maybe the second and third one, if I swapped the second and third equations and I asked you to solve this system, you're probably going to tell me, oh, it's the same solutions, right? Z is still equal to 4, y is still equal to 3, and x is still equal to 11/2. Of course, now it doesn't look like a triangle at all, right? So if somebody had given us this system, what we could have said is, well, I'm going to permute 2 and 3, right? And then get it back into this triangular form and then solve this by back substitution. This is how it's going to work. See what I mean? So you take something that's not triangular here and you do an elementary row operation to make it triangular so that then this first remark kind of comes back into play. Okay, let's see. So in other words, this just means it doesn't matter what order the equations are listed in. That's basically what that says. It's no big deal. The second operation is called multiply. So we can multiply the ith equation through by some constant. I'm gonna call the constant K. And K should be not 0. Obviously, if you multiply an equation through by 0, you'll lose that information. We don't want to do that. There's a notation for this that I'm going to want you to use, m sub I of K. So this is multiply the ith equation through by K. And I think you guys would all agree, for example, that if I took this system here and I just decided to multiply the second equation through by 10, that would be m2 of 10. Well, now z is still equal to 4, y is still equal to 3, and x is still equal to 11 over 2. We have not gained or lost any solutions in doing that. Okay, so those are two good elementary row operations, but there's one more, and the third one is actually, well, it's kind of the most complicated one, but it's also the one that we're going to probably use the most. It's actually pretty important. And this one is adding. So we are going to add K times the ith equation to the jth equation. So in other words, we take a multiple of one equation and add it to another one. And the notation for this, I'm going to use a capital A. This time, two of the equations are involved, both I and J, so I'll put subscripts of I, J, and then this is of K. So A sub ij of K. That is my third operation. So this one's maybe not quite as obvious that this would have no harmful effects on my system of equations, but suffice it to say that this is absolutely a safe thing to do. I'm adding a multiple of one equation to another equation. Notice that the first equation, the ith equation, actually does not change. Right? I'm using that equation to change the jth equation. It's actually the second equation that actually feels the effect of this operation. So the second equation, the jth equation, has K, which is any number you want, times that ith equation added to it. Okay, so that's kind of it. Obviously, we're going to practice this elementary row operation process today, and we're going to be using it pretty much for the entire semester. It's one of those things we kind of have to master it. But before I actually do an example, I think I'm going to write down my third remark. I said there's 3 remarks here. Is everybody so far so good? This will make more sense once we actually have an example and practice it. So I'll get to that in just a moment. But I'm going to make my third remark before I get any further along here. The third remark is just a quick one, which is that those first 2 remarks, the 1 and 2 above, the first 2 remarks above, right, they can be applied to the rows of the matrix A sharp. So this is nothing very deep. Guys, over here, my elementary row operations, I'm making references to equations, right? But remember that what we're really going to do is we're going to take our linear system of equations and put them into an augmented matrix. That's what A sharp is, right? You build this augmented matrix. We did this last week. All of the coefficients of the system just go into this matrix. And then instead of thinking about it in terms of the effects on the equations at this point, we can just think of it as operations on the rows of A sharp. Right, so that's all I'm saying here. It's nothing too difficult. Okay, so guys, the process that we're going to try to learn here and follow is we are going to use elementary row operations. This is how we're going to solve our systems. This is how we're going to solve our systems. We're going to use elementary row operations to convert A sharp, which is the augmented matrix for the linear system. We're going to try to convert A sharp into, well, you might be expecting me to write down triangular form, because that's what I was hoping to do originally. But of course, we need to be a little careful here because not everything is a perfect triangle. When I was talking about upper and lower triangular matrices in that short video that you watched over the weekend, those were all square matrices. But what if I have a linear system that only has, two equations, but they're really, really long, right? Like this. This is not going to be, upper or lower triangular because the matrix is like way, wide and not very tall. So we're not going to write the word triangular form here because that could be confusing. There's a different phrase for this, which is we're going to convert A sharp into what is called row echelon form. Row echelon form. And for those of you following my acronyms for section 2.4, right? Row echelon form is abbreviated REF. That is the idea. Okay, so I need to explain exactly what row echelon form means, like what is that form going to look like? And there's a definition for that. So let's write this down. A matrix is in row echelon form if there are two things. There's just two parts to this. It's a pretty simple definition. The first condition here, guys, is that all zero rows. So if you have any rows of the matrix that are just literally all zeros, they should be pushed down to the bottom of the matrix. So these are at the bottom. So those are at the bottom of the matrix. Any all zero rows, we just sort of stack those at the bottom. Well, what if they aren't at the bottom? Then it's not in row echelon form, but how am I going to get it into row echelon form? Let's say I have a row of zeros let's say the first row of the matrix is all zeros. What am I going to do to try to get it into this row echelon form?
Swap them.
Permute, right? I can permute or swap that row down to the bottom, right? You can just remember the first operation over here is basically saying you can put the rows in whatever order you want. So if there's an all zero row and it's not at the bottom, just permute it down to the bottom. Okay, so that's pretty easy. We can always make that happen. And then there's just one more part to the definition here. For all other rows, right? So for all other rows, the first non-zero entry which is called, by the way, there's a word for this. This is called a pivot. So in the lingo of, performing elementary row operations on a matrix, you'll hear the word pivot a lot. That first non-zero entry, a couple things about it. It must be a 1. Well, what if it's not a 1? What if it's a 7? So I'm looking at a row of my matrix and I got 0, 0, 0, and then a 7 shows up. I can, you're right, I'm gonna call it multiply that row by 1 over 7, right? So if I just multiply by the reciprocal of whatever this first non-zero entry is, I can turn it into a 1. Again, that's an ERO that we can use to achieve this condition here. It must be a 1. And there's another condition, and this is the most important part. It occurs to the right. It occurs to the right of the pivot in the row above. So these pivots have to kind of go down and to the right. Let me draw kind of the structure of this for you. Here's like my matrix. If I have any rows of all zeros, those have to be down here at the bottom. So I'll just go ahead. Let's suppose we have a couple of rows of zeros. By the way, guys, when you have a row of zeros in a matrix that's representing a linear system, it's pretty much worthless. It doesn't tell you anything. It's just there's no information about the unknowns that you're gonna figure out from this. So you might as well stack them at the bottom, okay? And then in all other rows, the first non-zero entry must be a one. Guys, please put like diamonds. This is a good habit to get into. I mean, it's technically not required and you won't see it always done in the books, but I like to circle my pivots or put diamonds around them. And then after that pivot, you can have whatever numbers you want. It does not matter. But then in the rows below that, the pivots, so here's the important thing, guys. The pivots have to go down and to the right. So in the next row, you have to have a 0 there. Because if you had another 1 here, then the pivot would not be to the right, it would be directly below. So that has to be a 0. And maybe you have several zeros, right? But eventually you'll get to a pivot that is in that second row further to the right. And then in the next row below that, now you might have even more zeros before you finally get to a pivot that's, again, down and to the right from the pivot in the row above it. So this would be kind of the structure of what a row echelon form of a matrix might look like. So I'll just kind of, you're going to see me use this notation. If I write REF of A, it just means the row echelon form of A. Okay, really good. So far, is everybody kind of with me? This is all of kind of the setup of the whole thing. I think we should do an example though. It does take some practice doing EROs, and I noticed last semester when I taught the class, there were some students who even 9, 10, 11 weeks into the semester were still kind of struggling with this, and that just makes everything harder because of course you're trying to learn new material at that time. So it's really important that we try to kind of get on top of this early. It'll just make your life easier as we get into the later weeks of the semester here. So let's try an example to practice this. Let's let capital A, I'm not going to worry about the A sharp part right now. I'm just going to take a matrix A. Let's say the first row is 2, -1, 3, 4. The second row is 1, -2, 1, 3. And the third row is 1, -5, 0, and 5. Say we have something like that. And let's find a row echelon form of A. Okay. Try to find a row echelon form. So, in other words, it's kind of like putting it into a triangular form. This is not really a triangle, but it's kind of in the same shape that you might be thinking of a triangle to be in. So for the solution, let me kind of give you some strategy points here, guys. The very first thing you should be trying to do is to get a 1 into the upper left corner of the matrix. There's only one situation where you wouldn't be able to do that. If you happen to have a matrix that was, you know, starting off, all of the rows started with zeros, well then permuting things or multiplying through by a constant or adding a multiple of one row to another, none of those things are going to change the reality that you have all zeros here. So in that case, you'll never get a 1 in the upper left corner. And in that case, you basically just want to kind of move to the right and start working on the next column. So in this case, though, it is possible to get a 1 into the upper left corner. And I'm wondering if anybody wants to tell me what ERO we could do that with. You want to take a stab at it, anybody? Yes, go ahead. Okay, I could permute 2 equations. Absolutely. So here's how I would like you to write this down. I would like you to write capital A, and we're going to use this little sideways S, which is like a little twiddle symbol. And next to the twiddle symbol, I want you to write down what ERO you are doing in that step. So at this moment, we are going to go ahead and permute. Is it Gwendolyn? Sarah. Sorry. So Sarah has suggested we do permuting. And what rows do you want to permute here?
You could do the second or third.
Okay, anybody have a preference? Third, okay, permute 1 and 3. So I'm going to do P1, 3. This just means I'm going to swap the first row with the third row. And I'm going to write down the new matrix. What we do here, guys, is we take the third row and we put it first. We take the first row and we put it third. Okay, so the second row actually does not change. So there we have it. And we've got a 1 in the upper left corner, and I now know that that is going to be a pivot that we will be happy with in that position. So I'll go ahead and put my little diamond around it so that I kind of know that I'm done with that. And you're going to notice from now until the end of my solution, that first row is never going to change again. We're actually really happy with how the first row is looking. That's a good first step. Now, I see sometimes people try to get like 1s in all of the rows. That part really isn't necessary. So like this 2 right here, don't let that bother you. What we really want to do next is get 0s below that pivot, right? Let's stick with focusing on the first column. I need to get 0s below this pivot. And why is that? It's because I need the pivots that are below to shift to the right. As of right now, if I circled my pivots, they would all be just right in the first column, right? So I need to get 0s below that first pivot. Does anybody have a suggestion? Okay, I'm gonna go ahead and start writing down the next step. I'm not gonna change the first row at all because I'm pretty happy with it. But does anybody have a suggestion about how I could get a 0 right there? Because that's actually what I want in this moment. I would like to get a 0 right here. Yes, Blake.
If we like add or subtract,
Let's
all
add,
constants
let's
change.
make sure we add. So we do permute, multiply, or add. But of course, if you want to subtract, just a little tip, you can add the negative of whatever the number is. Okay, so we can add a multiple of 1 row to the second row in order to get that to 0 out. Does anybody want to take a stab at it? I'm gonna go A of. First, go ahead.
Third row by -1/2.
We could do that, but we're not going to because we don't want fractions if possible. Actually, that brings up a good point. Guys, right at the very beginning, I could have just, when I asked you, how do I get a 1 in the upper left corner? If you had said, oh, I'm just going to multiply the first row by 1/2, that would not have been wrong, right? That would have been okay and you would have achieved it, but then you would have had all these fractions throughout that first row, and that would have been sort of, you'd be living with those fractions for the whole rest of the calculations, right? So let's try not to get fractions involved. So let's not use the third row. I think I heard somebody suggesting over here.
First row, multiply it by negative.
Okay, I can take the first row times -1 and add it to the second row. And this is the notation for that. The rows that I'm involving are the first and second row, and I'm using a -1 times the first row and adding it to the second row. Now we have to do a bunch of mental math now. I have to go across the whole matrix and take the negatives of the first row and add them to the second row. And excuse me, I can see here that negative of 1 added to 1 gives me 0. Negative of -5 added to -2 gives me 3. Negative of 0 added to 1 gives me 1, and negative of 5 added to 3 gives me -2. I'm doing this mostly in my head, and you guys can and should do that as well. So I'm taking the negatives of everything in the first row and adding them to the second row. Okay, now that's great. That gets me a 0 below that pivot. I'm happy about that. I also have a problem in the third row. Now, if you're not comfortable doing anything else in this step, you can just recopy the third row and then go on to a new step. However, sometimes it will save you some effort if you sort of multitask. You say, well, I'm going to do another ERO right now to fix this third row, because I also want to get a 0 down there. Does somebody think that they could see an elementary row operation that I could apply? Again, I have to go back to this matrix. Is there something I could do with this matrix to get a 0 into that third row? Yes.
Multiply the first row by -2.
Okay, I'm going to use the A operation with 1 and 3, but this time the multiple is -2. The way I'm figuring that number out is literally just by looking at these two numbers. I'm not looking at anything else off to the right. It's just these two numbers. I say this is, how am I going to use a 1 to cancel out a 2? I'm going to take -2 times that and add it to that number. So then I have to go across that whole row and apply that ERO for each column. So I take -5 times -2. -5 times -2 is 10. I add that to -1, I get 9. Okay, then I take 0 times -2, sorry, 0 times -2, I add that to 3, I get 3. And then I take 5 times -2, which is -10, and I add 4 to that, and I get -6. So this is what we would have. Okay. Guys, this is looking great. Now, I do want to caution you about what I just did something here that's a little risky, and people can sometimes take it a little too far. What I don't want to see somebody doing is, oh, I'm gonna add 1 to 2 with something, and then I'm gonna add 2 to 3 with something, and then I'm gonna permute 3 with 4, and then I'm gonna permute 1 with 3, and then I'm gonna multiply row 3 by 5, and I'm trying to do 4 or 5 things at once. It is way too much, especially if you start permuting rows, right? You've permuted 3 and 4. So, okay, multiplying row 3 by 5. Was that before or after you permuted it with row 4? Nobody's going to be able to keep track of that. So let's not get too hog wild crazy with this multitasking thing, right? Something like this is very safe because the 2 EROs that I did, they don't really interact with each other. They don't affect one another too badly, so I don't mind it. This is getting a little too crazy. Okay, so just a couple of steps at once is fine. If it seems easy for you to do that, you don't have to. You don't have to combine things into a single step. If you're more comfortable doing it one at a time, totally okay. All right, with that in mind, does anybody have a suggestion for an ERO that I could do now? Because I'm not in row echelon form yet. Any ideas what we could do next?
By second row by 3 and then add that to it. I mean, row 2, yeah, multiply by
So
row
it's
2.
so you're going to add -3 times the second row to the third row.
Yeah.
That's good. Now, some of you might be thinking, well, don't you want to make this into a pivot right now? I could multiply the second row by 1/3 and turn this into a 1. And I know that I do need to do that. But we don't have to do it immediately. Because of course, again, if I multiply the second row through by 1/3, I will introduce fractions into some of these other entries, and I just as soon avoid that as long as possible. So I like what Marco is suggesting here is that we can postpone that part of it, and instead let's do what he's suggesting is A23 of -3. So what is that operation? He's taking -3 times everything in the second row and adding it to the corresponding entry in the third row. So let's see what that's going to give us. The first row does not change. Recopy it. And actually, the second row also does not change when we do that operation. It's only the third row. And see, what Marco is thinking ahead is he actually kind of knows that this is going to be a pivot eventually, once I make it into a 1. That's going to become a pivot. And so he already knows that we need to get a 0 below that pivot. I mean, we also need to get a 0 here too. See, we already have this 0. But if I do this ERO and I take -3 times the second row and I add it to the third row, look what happens. The third row completely wipes out. It gets completely zeroed out. Yeah. Okay. And so then what would be my last ERO to finish this solution off?
Multiply the second row by 1/3.
Multiply the second row by 1/3. Now, of course, we will see some fractions, but hey, we've kind of already won the game, so who cares at the very last step if there's a fraction here? I can live with that. So we'll do a 1/3 here. The bottom row is all zeros, and we've said that any all 0 rows should be at the bottom, so we're already in good shape with that. And so I'm good to go. This is good. This is good. This would be a final answer. Okay. You know, one thing I should mention here, guys, also about all of this is that, I'll just call this maybe a little remark, is that the answer, the row echelon form of A, is not unique. Unique means like there's only one right answer. It is not a unique thing. And you can see kind of why that would be the case straight away here. Because if you go back to this example again, and if you let's say you multiplied row 1 by 1/2 to start the process off. So you go back to the original matrix. If you had multiplied the first row by 1/2, there's nothing wrong with doing that from a mathematical perspective. I'm not going to fill in all the rest of the numbers, but look what your first row looks like. And that first row is now done, right? We're not going to be messing with the first row anymore, and it's different than the first row that we got in our answer over here. So I can already see that this is gonna, if I had gone this route, I would have ended up with a different row echelon form. So the row echelon forms are not unique. Now, that's kind of good news and bad news with that. The bad news with it is, okay, so when you're doing the homework problems and you want to check your answer in the back of the book, and you look at your answer and you look at the back of the book's answer and they're not the same, that's kind of inconclusive, right? Because maybe the back of the book has this answer and you're coming up with this answer. Well, you could both be right. So the back of the book is a little bit less useful when there's so many correct answers. But I guess the silver lining, the good news is that, yeah, if you have something that's different than the back of the book, it doesn't mean that your answer is wrong. It's maybe just a different answer. The back of the book is only going to be able to show you one possible answer. Alex?
I'm just wondering, you know how we like that's simple for the pivot?
Yeah.
Do we don't have to do it like until the very, very end? Because there was like a one.
Right here?
for example, like even in the next one, because it's supposed to be to the right, right? So like,
Oh, like here?
yeah, like the one like in the, yeah, like why are we not,
Oh.
putting the little.
I mean, I could do this. I wouldn't be upset if you circled kind of where the positions were. Like the first non-zero entry in each row. That's also fine. Yeah, I just like to wait to circle stuff till it's in the right position at least. So yeah, be careful. I have also seen students do this. And this is really not good. If you had some matrix like this, I've seen people do this. They'll just kind of just go ahead and put diamonds down a diagonal of a matrix, which is kind of meaningless actually, because I don't have zeros below the pivots. This is not a row echelon form at all. So be a little careful about abusing this diamond notation for pivots, but yeah, this would be okay to kind of help you keep track of things. Definitely. Okay, so guys, the row echelon form of a matrix is not unique. However, there is one thing about it that is unique. Is that a hand?
Yeah.
Yeah,
I was
please.
gonna ask, for any given matrix, is there a finite amount?
Oh, that's a great question. Like, so is there anything we could say about the row echelon forms? You know, there's actually kind of an infinite number of correct row echelon forms that you could have. We have 30 people in this room. We could all take 30 different stabs at it with different EROs and come up with 30 different row echelon forms. But you know what? All 30 of those row echelon forms would have one thing in common. They would all share one thing in common, and wondering if anybody knows what that is. So all correct row echelon forms will share one thing in common. And this is a way to at least partially check if your answers are correct. Like you can look in the back of the book at their answer, you can look at your answer, and if they at least have this thing in common, that's kind of a good sign. Does anybody remember what this is, or does anybody have an idea what this could be? What do you think all of these row echelon forms would have to share in common? Johnson? The first row? Not necessarily. See, here's a first row that doesn't look like this first row. So the first rows can be definitely different. Yes, Mohammed?
Would it be the pivot position?
The pivots, I'm glad you're talking about the pivots, not necessarily the positions, but the number of them. The number of pivots will always agree. All 30 of us, if I send you all off to solve this problem your own way with your own EROs, when you finally get to a row echelon form, there's one thing that everybody should agree on, and that is the number of pivots. This is such an important concept. The number of pivots, and this is called, there is a name for this. We can think of this as a definition. This is called the rank of the matrix. The rank of A. The rank of a matrix, that is how many pivots are there in any correct row echelon form. So in this example, I'll just say in the above example, what would be the rank of the matrix A that I gave you here at the top of the board? It would be 2, right? It would be 2. Why do I know that? Because I look over here and I see I have 2 pivots. I have 2 pivots. That's called the rank of the matrix. And no matter what EROs you happen to choose to do, you should always get the same number of pivots, the rank of the matrix. Really important. We're going to be talking about the rank a lot this semester. It comes up in many places. Okay, so there is kind of that uniqueness about that. That's something that's in common to all of these row echelon forms. Okay, questions so far? Okay, so this was just a little baby practice with doing the elementary row operations. Of course, why we really want to do elementary row operations is that we would like to solve a linear system of equations somewhere along the line. So I'm going to, during our 10-minute break, which I actually am going to go ahead and take it a little early today because this is a good stopping point. Let's take a 10-minute break, and during the break, I'm going to write a problem on the board, and then when we come back from the break, we're actually going to go through the full process of using these EROs to solve for the unknowns in a linear system. Okay, so that's going to be good to practice that. Let's take a 10-minute break. I have about 10:50 on my clock here, so at about 11 o'clock, we'll pick things back up again.
Thank you very much.
I can't take small naps like that. My naps have to be like 2 hours. I know. You know, Steve, but there's one. Oh, really? Oh, yeah.
Well,
Yeah, I mean. I go up and find out. I was in Ireland last week.
oh, okay, so I was wondering if you got mixed up about the class or something, or decided you weren't gonna take it. Because I just about gave out all my outputs to add you, so, because last week I took attendance and you didn't email me or anything. So, not so good, but I think what has to happen is I have to send the math department an email giving you permission to add. They will then have to check if they can do that. And now I'm putting pressure on them to do it today, basically. Because I sent in all these add forms last week. So now I'm at almost I don't even have room in the class. There's a lot of, although it's a lot of people missing today, but see if they're on the roster, I have to count it as they're here. And also I can't over enroll this class. I tried to do that once. I tried to say, I'll take a couple of students, but then the math department, so then I can't do that because there's only so many people allowed in this room because of the fire code. So I will have to send them an email. That means you're gonna have to be ultra on top of this because you have to add by tomorrow. So which really means I need to send these emails today. But I have a very busy day today. So you're going to need to follow up with me on the hour, every hour, maybe not quite, but you know what I mean, like this afternoon, tonight, whatever, you need to, oh, have you done that? And I mean, I'm gonna try to remember to do it when I go upstairs right after class, but I also have office hours. And that takes me a little while to send an email. I have to at least write down your, oh no, actually, I have your CVIT because you're on my waiting list. Okay. So I have what I need to send them about you. I think I just need to remember to do it and find.
Yeah, I'll send you like.
Cause it takes me an email to send. So if you have not gotten something from the math department, by the time you go to bed tonight, I would write out an email to me before you go to bed tonight instead and say, did you send in the ad permits request to this department? Because, yeah, we've got to get this done. Otherwise, if we don't get it done by tomorrow night, then it's a major hassle. Trust me. Provost has to sign it, dean has to sign it, chair has to sign it. Even if I'm all good with it, 3, 4 other people have to be okay with it also, and you have to pay like $20 at least. I forget what the fee is. So let's try to get that done. Okay,
I'll send
and
you-
have you caught up on all the work?
Yeah, I did all the,
You submitted the homework? and-
I submitted the homework as well, I was out.
Okay.
I also did the notes. for
Okay,
that.
at least I had you on Canvas, so you were, and you watched the videos,
Yeah,
or at least you have them. Okay, very good.
Christmas and New Year. No.
You change Blackstone, Blackstone going to.
No. No, whatever. Not myself.
Hey, yeah.
I might be wrong, but I think the drop date's today.
Today, I thought so as well.
Yeah,
The 10th.
I just wanna let you know, cause I heard.
Oh, today is the 10th. Oh my gosh, you know what? I have, for the last 4 semesters, I've been teaching Mondays and Wednesdays. And now this semester I'm teaching on Tuesdays, Thursdays. So I'm used to it being one more day. You're absolutely right. It is today
Yeah, just to.
for you. It all has to be done today. That is going to be really interesting. So we're gonna be depending on the math department. I'm gonna send an email and then we have to get this done by 5 o'clock today, that they give you an ad permit, which you then have to use by midnight tonight. You have to use it by midnight, but before you can use it, you have to get it. And to get it, the math department office has to take a step that depends on me, you see. No, you'll get an email from them that'll have it on there, but that'll only happen whenever they. Yeah, that's why you don't wait till the last day to have class to check in with your professor about it. Yeah, I even wrote it on my sheet. Today is the last day. I just don't know why I said tomorrow. It feels like Monday to me. See, on Mondays, I don't have class. So this is like my Monday.
Can you see? It feels worse than lipstick. So at least lipstick, it's like, okay, it's good lipstick. That just looks like it's dry, but it looks so nasty. It's okay. It makes sense that it- That's the delicious. Very nutritious.
Just like the compass, I mean. We're like 95.
Like, actually, we had not only so much here, but the table. Yes, basically, I'm like,
And then put it on.
Guess, like,
On my journal.
walking in the class was a nightmare. Like, walking into my class was like, all the tables, no, the tables were like everywhere. There was no rows of columns.
Or like some.
It was just
like the
chairs.
stand lines.
And I put my, I don't know if
You know, you just like.
so I wouldn't roll over it.
Or like a little logo.
Most of the time.
Oh no. Just roll. Thanks.
Now you fiction.
Another friend told me.
Yeah.
That I like it. I got like one.
That's what I was thinking when I was doing that, so I was thinking, the homework. No, homework two.
Yeah. I
I
mean.
was like, this feels like homework two, I hate it.
Another water bottle.
Granted, it's easier now.
Back in the-
I like that, I like this better. Oh, me too.
Yeah, I never had it.
How'd you feel about Calc 3?
And page like.
Oh, just kidding, I like Calc 2, I hated Calc. I forgot, I was the exact opposite. Calc, okay, my favorite was like Calc 1, because that was me. Then it's really.
It's starting from that.
Yeah, Calc 2 was my least favorite. I hate it. I hate it. No, Calc 3 was way better. You're my daughter. I didn't hide from that. Yeah, I guess that's fair. We already learned to interest about it. But I was like,
The only thing I have.
and then the search.
Oh,
yeah.
I really don't like it.
It's not. It was like. Wasn't it related rates and comments? We like connect.
So.
That was your fault.
I was
All right, guys, maybe I'll go ahead and pick things back up here again, and we're gonna start this section 2.5 in just a moment, and we're gonna do this example that I've got on the board. I also wanted to remind you to thank those of you who have stopped by my office so far, either in Zoom or in person, just to say hello. It is helping me learn your names much better that way when you kind of come by in small groups or whatever. And I have extra credit sort of associated with that if you do it by next Tuesday. So there's still some of you I don't think I've had a chance to stop by, which is fine. But I would love it if you would come by and just 5 minutes, just want to find out a little bit about you, see if you have any questions, make sure everything's going smoothly and all that kind of stuff. If you do that by next Tuesday, what I'm going to do is I'm going to, so believe it or not, in my SOQs for my teaching for this class, a lot of students in the past have said, gee, I wish we had quizzes. They were like, we need to like test our understanding and everything. And, you know, I don't give a lot of quizzes there. That is the truth of the matter. The only reason I don't is because I just don't have a lot of time for it. We have so much material to cover. I just can't give that much time to it. So what I decided to do instead of like giving a quiz in class is I would sort of like a week before we have an exam, like make up a mock quiz to like pass out to let you at least get an idea. Okay, we're not going to spend class time on it, but at least you can like practice like what kind of questions there would be. And so what I have tended to do is offer extra credit for people to do the mock quiz and turn it in. It would be like on top of the homework. So you do have to put the time into it. But what it says in my syllabus is I'll let you do that as long as you have stopped by to say hello and introduce yourself. So if you want to be eligible to do these, isn't that funny? You have to like come in to say hello so that you can be authorized to take quizzes. It's kind of a weird thing, but I decided to do that. So stop by within the next week so that you'll be on my list of people who can get extra credit by doing a mock quiz before we actually take an exam. And that'll be something that you would then do on your own time. I wouldn't give you more than a day or two to do the mock quiz, because after all, it's just like a couple questions, one sheet. It's a quick thing. But anyway, so that is going to be coming. When we do have an exam actually a couple weeks from now. I'll talk more about that on Thursday, I think. For right now, I think I'm gonna try to finish up this discussion that we were talking about here, which is section 2.5, Gaussian elimination, okay? So let's imagine we wanted to solve this linear system. I probably should add, if possible. Because remember, it's not always possible to solve a linear system. But let's see if we can take this set of equations and solve it. So what do you suppose my first step is going to be? It's the running joke of Math 250B. What is the answer to every problem in Math 250B? Put it in a matrix, right? We're basically going to do that over and over again all semester long. And this time it really is an augmented matrix, so I'm going to call it A sharp. And we're just going to set this into an augmented matrix. So 2, -3, 1, -1, 1, and then augmented with 0. That's the first row. And then the second row is 4, -6, 2, -3, -1, and -5. And the third row is -2, 3, -2, 2, -1, and 3. There's my A sharp matrix, okay? And we're going to remember now that we will not gain or lose anything by performing elementary row operations on this matrix, right? So that's what we're going to do. We're going to basically take this matrix and do the same thing that we did on the example before the break. Does anybody want to suggest? Remember, the main goal here is to get a 1 into the upper left corner. Okay, that's ultimately the main goal. However, right now we don't have any 1s in this first column at all, so we might need to, we can imagine multiplying the first row by 1/2. But see, we don't have to do that right away. We can postpone that, avoid fractions as long as possible, and just live with this 2 right here for the time being. Can I somehow, if I'm kind of thinking about it in those terms, that I'm going to leave that 2 there, I'm just going to actually leave the whole first row the way it is. Even though technically a 2 is not a pivot, what I really want to make sure I'm accomplishing right now is getting zeros below where that pivot eventually is going to be set up. So I want to try to get these 2 zeros. Does anybody have an ERO that will get me a 0 right here in this position? Yes, go ahead, Jason.
So you would multiply the first row by -2 and add it to the second.
So it's A of 1, 2 of -2. Exactly. Guys, let's take a look at this. All he is doing is looking at these 2 numbers. And he's saying, how can you use a 2 to zero out this 4? Well, you take -2 times 2 and add it to 4. Okay, so now we have to go across the entire matrix, all of the columns, taking -2 times whatever's in the first row and adding it to the number that's in the second row. So we get a 0 here. -2 times -3 is 6. I add that to -6, I get 0. -2 times 1 is -2, and I add that to 2, and I get 0. -2 times -1 is 2. I add that to -3, I get -1. 1 times -2 is -2, and I add that to -1, I get -3. And 0 times whatever, I add that to -5, I get -5. So there's the second row. Question?
When you're multiplying row by a number and adding it to the next row.
Yeah.
Should the row that you're multiplying that number always be the row?
Oh, you've probably noticed, a good point. You've probably noticed that I've been adding higher rows to lower rows. You don't have to do that. You don't have to do that. If you're doing this process sort of in what I would call the most natural way, you should usually be adding higher rows to lower rows, but it doesn't have to be that way. Good point. Good point. Okay, and then how can I achieve a 0 in the lower left corner? Using the matrix that's over there. Alex?
You could just add the first row.
Add the first row to the third row. That would be just taking 1 times the first row, which is just the first row, and adding it to the third row. So exactly right. I'm going to add the first row to the third row. That look okay?
what if we do half of the second row? We
You
take the
you could
fraction.
take half of this second row and add it to the third row as well. I don't like that as much because I'll end up having to deal with some fractions. And I would rather avoid the fractions. It's much better actually in this case to do this one. Because if I just add the first row to the third row, I won't have any fractions. This is the kind of thing that you will get used to with some practice. So I'm just adding everything in the first row to the third row. Add the first row to the third row. That's what I get. By the way, guys, this is going to be what you're doing for Sunday's homework, Sunday/Monday. And this assignment will be a more, so the one you're doing for Thursday is pretty straightforward. This one's going to be more tedious. You're not going to want to do, I never like to do EROs when I'm tired, when I can't focus, when I'm stressed or whatever. Like this is something that you really do have to have your brain totally into. It's not like it's hard math to like add a multiple of a row to another row. But if you're trying to do it when you're like half awake in a zombie mode, there's a good chance of making a mistake. And I bet you know what happens when you make even a small little mistake, like even at the first step, those mistakes just proliferate through the whole rest of your solution. And it's frustrating because then you're just not getting it to work out correctly. So you do want to take some care with this problem. I'm going to go ahead. Somebody was asking me earlier about circling pivots. If you want, if it helps you, you can go ahead and kind of identify where the positions of those first non-zero entries are. And that'll help you to figure out what you maybe want to do next. Okay. Does anybody want to suggest an ERO that I can maybe do from here? Eduardo?
Swap the second pivot.
Yeah, why don't we do that? Let's permute rows 2 and 3. And I'll go ahead and do that. So the first row stays the same. 2, -3, 1, -1, 1, augmented with 0. And now I'm going to put the third row second. So 0, 0, -1, 1, 0, augmented with 3. And then I'm going to put the second row on the bottom. So 0, 0, 0, -1, -3, augmented with -5. Okay. And now I actually have the pivots in the correct alignment for the rules of row echelon form. What's the only thing left that I have to do here? Turn those pivots into ones. Exactly. And that I can do easily by just using the multiplication operation. So I can multiply row 1 by 1/2. I can also multiply row 2 by a minus sign and row 3 by a minus sign. And I don't mind if you do all of those at once because they're kind of operating on separate rows independently of each other. So the first row is 1, -3/2, 1/2, -1/2, 1/2, augmented with 0. The second row is 0, 0, 1, -1, 0, and -3. And then the bottom row becomes 0, 0, 0, 1, 3, and then augmented with 5. So that's what you would have. You with me? And that is a row echelon form. By the way, what is the rank of this matrix A?
3.
It's 3 because I have 3 pivots, right? The number of pivots is called the rank of the matrix. So this one has a rank of 3. Now, notice that we did eventually have fractions in the matrix, but not until the very last step. So it wasn't such a headache to keep track of the calculations that way. So it's always nice to postpone fractions as long as you possibly can. Now, guys, from here, I have row echelon form. And now supposedly one of my remarks from earlier is that the system is easy to solve by back substitution if it's in this triangular form. So I'm going to show you how to do that next, okay? The first thing I want everyone to realize is that this matrix still corresponds to a system of equations. In fact, we don't actually need to do this, but I'm going to just this once to show you what that system would look like. So the first row would correspond to, u minus 3/2 v plus 1/2 w minus 1/2 x plus 1/2 y equals 0. The second row would be w minus x equals -3. And the bottom row would correspond to x plus 3y equals 5. right? So you can go back if you want to. This turns out not to be that important to do this. But I just wanted to point out, we still have a linear system here. And we don't want to lose track of it. Okay, so guys, now remember, no solutions. No solutions to our original system here have been gained or lost in anything that we've done. So whatever the solutions are for u, v, w, x, and y here are the same as the solutions for u, v, w, x, and y over here. And this is somehow, you know, a little more like a triangle. Okay, I'm not saying it's a perfect triangle right now, but it's a little more of this so-called triangular form, which is the row echelon form. Okay, question? Yes.
So that system of equations is currently in triangular form?
It's in row echelon form. Let's say it's in, there is no such thing really as triangular form. I kind of put it in quotes over there. It's just kind of the way I'm casually talking about it. So guys, how are we now going to solve this by back substitution? I mean, the one that we started with way over here was easy. We just said z equals 4. We plugged it in and went back to the previous equation to solve for y. And then we plugged it in and figured out what x was. This is a little harder to understand because there's like 5 different letters floating around in this problem. So I'm going to write down a definition here of a couple of terms that I think will help us talk about this. Notice that the pivoted variables, which are the ones aligned up with the pivots, are the u, the w, and the x. The variables corresponding to pivots are called leading variables. Those are called leading variables. So in the example that we're doing right now, that would be the u, the w, and the x. Okay. And then the other variables, corresponding to what I guess I'll just refer to as non-pivots. The variables corresponding to non-pivots are called, these are called free variables. So we have leading variables and free variables. Every variable is either a leading variable or a free variable. And on this example, the unpivoted variables would be the v and the y for this problem. So we have 3 pivoted variables, which are called leading variables, which are the u, the w, and the x. And the free variables are the v and the y. Johnson.
I just have a question about the matrix.
Uh-huh.
How do you know you finally got into the row echelon?
Yeah, so the row echelon form, we kind of have to go back to the definition from the first part of our class today, which is basically that any rows of all zeros have to be at the bottom. There are no rows of all zeros here, so we don't worry about that part. And then the pivots, the first non-zero entry in each row has to be a 1, which is why we didn't stop here. We had to go do one more step to make them all 1s. And then the pivots have to drift down and to the right somehow. They don't necessarily have to cover every column. In fact, they can't cover every column here because there's too many columns compared to how many rows we have. So those unpivoted columns are what are giving rise to these free variables. Guys, when you're setting up these matrices like this, I want you to kind of think of the columns as being aligned with these unknowns. So each unknown is sort of associated with a particular column. And the pivoted columns correspond to the leading variables. That's u, w, and x. The unpivoted columns or non-pivoted columns, those are the free variables. And guys, when we say that they are free, when we say that we are free, we mean exactly that. They can take on any values whatsoever that we want. Okay, we can let them be equal to anything. Okay, so now I'm going to show you sort of this modified back substitution method. Over there on the one way on the far left of my board, it was really easy. Here, it's not quite as easy because we have these free variables, right? So here's the way we're gonna do this. What we're gonna say, guys, is we're going to let y. I'm starting with I am doing back substitution, so I'm gonna start at the very bottom. I see a free variable, it's y, and I like to use a new name to call my free variables. So I'm gonna call it t, and I'm gonna write the word free next to it. Now, there'll be some people who say, well, why did you do that? Well, why don't you just call it y? It is y after all. So why are you saying y equals t? The reason is this. Every time we do a problem where there are free variables, I like to use the same names for those free variables every time. I will usually use an R, an S, or a T for a free variable. And it just helps me get into the rhythm of doing all of these problems kind of with the same approach. So if you see a T being introduced as a free variable, you'll feel like, yeah, I've seen that a lot, right? I've done that many times. So we'll go ahead and do that. Now, once we've established y as a free variable, let's continue with the bottom equation here. We can actually solve for x. X would be equal to 5 minus 3y, but I want to re-express it in terms of my free variable. So I'm going to write x as 5 minus 3t. Okay? So in other words, if you tell me that you want t to be equal to 10, remember it's free, it can be anything. That's fine, but x is not free, right? Once you've decided what t is equal to, x is forced to be equal to whatever 5 minus 3t is. So if t is 10, then x must be negative 25. Right, there's no choice about that. Okay, now that kind of takes care of the bottom equation. And the next thing I'm going to do is, sorry, I don't want let, I want then, I'm going to go to w. So by back substitution, I can solve for w. You see here that w, if I isolate w on that second equation, it should just be x minus 3. Which means I'm going to just subtract 3 from what I had for x. So 5 minus 3t, if I subtract 3 from that, it's 2 minus 3t. So that's what w equals. That's this middle equation. Okay? So I've talked about y, I've talked about x, I've talked about w. Let's keep working backwards now. When I get to the top line, I have another free variable. And so I'm going to call that one v. And I'm going to use an r for that. Again, I like to use r, s, and t for my free variables. So you'll see that throughout the book as well. So that's another free variable. Please don't use the same letter that you used for y because there's no reason why v and y would have to be the same number. So I want to have two different notations for that. And then finally, I can solve for u. U is a leading variable here, right? And what is it? Well, if I solve that top equation for u, I get 3/2 of v minus 1/2 of w plus 1/2 of x minus 1/2 of y. And of course, I want to, again, write everything in terms of the free variables. So I would be rewriting this as 3/2 of r minus 1/2 of the quantity 2 minus 3t. And then plus 1/2 times the quantity of 5 minus 3t. And then minus 1/2 of t. And lastly, we should probably try to simplify that a little bit. I'll save you the headache of that and just kind of tell you what we're going to get here. This is going to turn into 3/2 r, right? And then it actually becomes minus 1/2 t. And then there will be a plus 3/2 as well on the u variable. Okay? So that is your solution for u. So if you give me a value for t and a value for r, we can now figure out what y, x, w, v, and u would be for that. And in fact, now I'm going to write down my solution. I think I'm going to do it over here so I have just enough room here. I'm going to write down my solution to this linear system. And this is the notation I want to see, okay? So don't just do all this chicken scratch over here and then just kind of leave it. Let's clean it up into a nice answer, right? I'm gonna use my braces again, right? You already saw me do that once over here, right? These nice braces to set up my set. And I'm just gonna start listing the various solutions. Just please try to do it in the order that the unknowns are listed. So the first one is U. And so in the parentheses here, I have 3/2 R minus 1/2 T plus 3/2, right? That's the U value. And then I'm going to put a comma. The next slot should be the V slot, and we've replaced V with R, comma. The next slot would be W, and that's 2 minus 3T, comma. The next one would be the X, which is 5 minus 3T, and then comma. And finally, the Y variable was written as T. And then we can close our parentheses. Okay, so this has 5 unknowns, right? As opposed to the 3 unknowns in the first example over there, right? Here we have 5 unknowns, and not only that, these unknowns involve free variables. Okay, so it's a little bit messier than the first one on the far left over there. And then we're going to use this sort of math notation that's kind of standard. I'm going to use a little colon. The colon just means, if you were to read that out orally, you would just read it as such that. Okay, so it's this set of 5 entries such that, and then we list our free variables, which are R and T, and then we use another little funky math symbol, which is this sort of epsilon Greek letter, and this just means belongs to, and then we put our big real number set, which I'm sure you guys have seen before, in there, because the values of R and T, I assume that they're supposed to be real. They should be real numbers. Is everybody comfortable with how that notation looks? So, I have a question for you. How many solutions does this linear system have? Was it possible to solve it? And if so, how many solutions do we have? We have actually infinitely many solutions here. Because after all, you can choose those free variables to take on any numbers that you want, right? All 30 of us could pick 30 different values for R and T, and we'd all get a 5-tuple of U, V, W, X, and Y values that satisfied our system of equations, right? This system has infinitely many solutions. Let's just write that down. So this has infinitely many solutions. And they're all just indexed by the R and the T, which are the free variables. Does this kind of make sense? Okay. Whereas, the system over here, of course, only had one solution. Oh, what's the difference? Well, over here, I didn't have any free variables. Right, over here, every one of those variables, actually, if you did, I'm not going to talk, if you did put this system into a matrix, right, into some sort of an augmented matrix here, notice that your X, Y, and Z columns are all pivoted, right? They are all pivoted. So variables corresponding to pivots are leading variables. There's no free variables over there. That's why there's not infinitely many solutions over there. So if you're trying to decide whether there's going to be infinitely many solutions to your system or not, really what you want to ask yourself is, are there any free variables or not? If there are free variables, you're going to get infinitely many solutions. Kind of how this works. Now, it's also possible to get no solutions to a system. Maybe I should show you one example of that, the sort of 0 solutions possibility. Let's just run through the Gaussian elimination. I'd like to show you what happens, what goes wrong when there's no solutions. Yes?
Sorry, before we.
Uh-huh.
It says this has infinitely many solutions.
Yes.
We're still. Can't just like throw.
Oh yeah, you can't throw any numbers in you want. No, you can choose any numbers for R and C, but then these leading variables have to be evaluated with those values of R and T plugged into them, and you won't be able to just do willy-nilly whatever you want with that. You'll just have to work out these numbers.
So how do we know that they're like are right?
Okay, I'm not quite, so the R and the T can be any real numbers, they can't be wrong.
Yeah, but like X, Y, W, and B, they can be wrong, correct?
Well, okay, so so what's your favorite number what's your favorite number?
5.
5. So if T is 5, right, then I can say, okay, well, that's what Y equals. And then I can figure out what X is. If I plug in 5 for T, this is 5 minus 15, that'd be negative 10. And I know that that's right. I know that that's the correct value. For this choice of T, that's the correct X value. And then W would be, 2 minus 15, that'd be negative 13. Like I know all these are the right values that go with this choice of T.
So it has infinitely many solutions because the variables above it are dependent, or the variables below are dependent on the variables above.
It's infinitely many solutions because there exists a free variable, which you can choose, like your favorite number was 5. Well, my favorite number might have been 8. So if I plugged in C equals 8, I would get a whole bunch of different values for X, Y, Z, U, and V, and that's also a correct solution too, right? So everybody in this room could pick their favorite number for T and for R, plug them in, and we could have 30 different answers here. And of course, then we could take everybody on campus to do the same thing and get 40,000 answers here, right? There'd be no limit to how many correct answers you could have. Good point. Yeah.
So it's basically just like the leading variables are like they have a unique definition, and then if they're free variables, so they're the set of real numbers, so that is just an infinite set.
Yeah, the free variables, they really are free. They can be any numbers that we want. But then I think what Blake is saying is that, well, then what about the other variables? The other variables then do have prescribed correct values based on the free ones that you've already chosen. That is true. That is true. Let's take a look at something really silly. Here's my system. That's my linear system right there. I would like to solve it if possible. So I'll just say solve if possible. So is it going to be possible? I sure don't think so. I sure don't think so. And let's just see how would it play out. Let's just play dumb for a second. Let's just like pretend like we don't know that. Let's just write down the A sharp. Right, the A sharp would be 1, 1, and augmented with 1, and then on the second row it would be 1 and 1 augmented with 2. Right, so this would be the setup. This is a very small matrix. Here's X, here's Y. Okay, those are the variables that coincide there. And of course, I'm going to do EROs here. What would be an ERO that I've already got the first row in good shape. What would be a nice ERO to kind of work with on this matrix? Okay, I'm going to say add -1 times the top row. This is the A operation. Add -1 times the top row to the second row. That just means take the negative of the first row and add it to the second row, and look what you get. 0, 0, and 1. Okay, well, that's already in row echelon form, so there's no more EROs to do. The question is, what conclusion are we going to draw from this? Well, if we now go back, like we remember on the previous example, we went back and rewrote out the system once we had it in row echelon form. If we did that here, the first row would be X plus Y equals 1. And the second row would be 0 times X plus 0 times Y equals 1. Right, that's how you would read the second row in this row echelon form. And I think everybody can now understand that we're getting to an impasse here because this is obviously 0 added to 0. There's no way that that would ever be equal to 1, right? You can't find values that would work. And so what's really wrong with this row echelon form is that we have a pivot in what I'll call the far right column. So if you get that, right, if you get a pivot that drifts all the way beyond the bar, into that far right column, that always implies that the system is not consistent. It has no solutions whatsoever. Okay? It has no solutions whatsoever. All right. Make some sense? So we've done one example where there was exactly one solution. Then we did this longer example here where we actually had infinitely many solutions because of the free variables that showed up. And now here we have a system with no solutions. Believe it or not, guys, those are, in a nutshell, all of the possible outcomes. Every linear system will either have no solutions at all, or exactly one solution, or infinitely many solutions. That's worth summarizing in a quick little remark here. So I'm going to go ahead and write this down first. Mark here is that every linear system must have either zero solutions. Let me write down what that would look like. That would be if there is a pivot in the far right column. That's how you would end up in that scenario. Zero solutions is one possibility. One solution is the second possibility. And what would be the characteristics of having one solution? Well, you would want to have no free variables. And no pivot in the far right column. So this just means basically what this means, guys, is that every column has a pivot, except in the far right column, you shouldn't have a pivot. All right, so maybe over here on the left, let me kind of draw the scenario out. So this would be, I've already kind of talked about this one. You get a pivot over here somehow. That's the zero solutions case. One solution case would be like this. There's no pivot in the far right column, but you also have no free variables. Every column is filled with pivots. There's no unpivoted columns with which to make free variables out of, okay? And then the last and final scenario, which we've also looked at already, would be infinitely many solutions. So you could have infinity solutions as well. And for this one, you do want to have free variables. Free variables occur, and also no pivot in the far right column. Okay, so I can't draw sort of a one-size-fits-all matrix form here, but I can just give you an idea that, maybe what you would have is, some columns over here that correspond to free variables. Your row echelon form would kind of look something like that. Okay, so those are the outcomes that you can have. And actually, it's the only outcomes that you can have. There's absolutely nothing else that could possibly happen. That's it. That's the whole thing. So you can't have a linear system that has exactly 17 solutions or 28 solutions, right? Every system will either have zero solutions, exactly one solution, or infinitely many solutions. And looking at these sort of visuals here, along with kind of the explanation, that kind of helps you delineate this trichotomy of cases, this trio of options that you can have. Okay? What do you guys think? Does this make some sense? I should not have erased that system that we were looking at earlier because I wanted to show you one other thing about it that's pretty cool. So let me just go back and write it down one more time. Okay, so just recall the system that we were just working with. be honest, I don't even remember it myself, so I'll get my notes out here and write it down again. This was the system, a 2u minus 3v plus w minus x plus y equals 0. And then 4u minus 6v plus 2w minus 3x minus y equals -5. And then finally, -2u plus 3v minus 2w plus 2x minus y equals 3. So this was our system that we played with a few minutes ago, and this was the one where, yeah, we got free variables to produce infinitely many solutions. That's right. Okay. Is everybody good so far, by the way? By the way, this whole technique that I was just explaining is called Gaussian elimination. It's basically where you're using EROs to bring an augmented matrix into row echelon form and then solving it by back substitution. Introducing free variables if necessary. That's called Gaussian elimination, really section 2.5. Okay. But what I want to do next is I'm going to propose something a little crazy. And have maybe another idea about how we could solve the system instead. It's going to turn out it's going to crash and burn. It's not going to work. But I'm going to at least throw something at you and see what you think about it. So far today, we have not done a lot of matrix operations. We've been mostly doing these EROs over here. But we do remember from last week that with matrices, we can do addition, subtraction, scalar multiplication, and multiplication. And believe it or not, I can rewrite this system in a different way that takes advantage of matrix multiplication. So let me just show you how that works. I know that I explained it last week, and then over the weekend, you might not have been doing the homework yet for chapter 2, but I'm going to remind you how matrix multiplication works, because we can actually rewrite this system in a different way. You ready for this? This is pretty interesting. What I'm going to do is I'm going to make a matrix out of these coefficients. So the first row is exactly what it was before, except I'm not going to put the right-hand side value in this matrix. So here I'm just putting the coefficients from the first row. And you know what I'm going to do? I'm going to remember from last Thursday that dot product method of doing matrix multiplication. Here is a row that I could dot with a column that has U, V, W, X, and Y in it. Well, if you actually, okay, I have not filled in the rest of the matrix yet, but if I was going to like multiply this matrix times this matrix, remember how that worked? We would pick a row of the matrix on the left and we would dot it with a column of the matrix on the right. Well, here I only have one column. If I dot that column with this row, what do I get? I get 2u minus 3v plus w minus x plus y, which is exactly the left side of the original equation. And of course, now I'm going to use an equal sign and put my 0 on the other side. Okay, and now you can see what I'm going to do. I'm going to fill out the rest of this matrix by using the coefficients from the second and third rows. So if we do that, guys, if we do that, and then the right-hand side, we can put these numbers in over here. If we do that, we are rewriting our linear system. I'm not doing Gaussian elimination anymore. I'm not doing Gaussian elimination. Gaussian elimination would start from A sharp, right? A sharp. You would take this system and augment the far right column, and you wouldn't be setting up a matrix multiplication. So I'm now teasing you with another idea about how to solve for U, V, W, X, and Y, which are my unknowns. And that little teaser that I'm giving you is I'm saying basically, instead of A sharp, let's just write down A, which is the coefficient matrix only, and we're multiplying that. This is under matrix multiplication, right? So we do dot products this away and this away. And we're multiplying that by this vector right here, which we can think of as a matrix. It's a 5x1 matrix. I'm gonna write it though in a notation that reminds me of vectors from calculus by putting a little arrow on the top of that x, and x is my unknown. And then on the right-hand side, we have this, what's called the right-hand side vector. I'm just gonna think of that also as a vector, and I'm gonna use a b for that, a little b. So this is my linear system. Let me write that up here a little higher where everybody can see it really good. Right, so in other words, what we have, so this is a coefficient matrix times a vector of unknowns equals the constant vector of values on the right-hand side. And my goal with this is to solve for x. And so my brilliant idea about how I could maybe solve for x, instead of doing EROs and so on, which by the way is going to be an idea that is going to crash and burn. It is not going to work, but my idea is going to be, if I wanted to solve for x, yeah, if you give some 10-year-old an equation and ask them to solve for x, right? I don't know what age they learn how to do this, but anyway, at some age, whatever age it is, right? They probably figure, oh, I just divide by whatever's in front of the x, and that allows me to isolate the x. Right, and so the tempting thing to think here is, ooh, could we solve for x by just dividing by capital A? And this was this big bummer I mentioned last week, that we can add matrices, we can subtract matrices, we can scalar multiply, we can multiply, but the one thing, the one operation that I didn't put in that list last week, which is the one thing we would want to do right now, is divide by a matrix. So sadly, I don't get sad very easily when I'm teaching math classes, but sadly, we cannot divide by A to solve for x. We can't do that. However, you know there has to be some kind of silver lining. I wouldn't just be giving you all this bad news with nothing good to say. In this particular case, yeah, there really is no hope for this idea over here. If I gave you this linear system, you should just do what we did earlier. You should do the Gaussian elimination. That is the go-to approach. But in some situations, right, there are some nice situations where we can do something like this. Okay, so I will say, however, in some situations, we can do something like this. It's not literally dividing by a matrix, and I would hate to call it that, but in some situations we can do something that's kind of like this. And let me, just got a couple minutes here left, but I think I can at least give you a little window into what it is, and then we will actually find some success with this idea on Thursday when we come back to it. But instead of dividing by a matrix, which we don't want to talk about, what we're actually going to do is multiply by a so-called inverse for the matrix. Now, not every matrix is going to have an inverse. This matrix will not have an inverse. That's why I keep saying there is no hope for this approach with this matrix. But sometimes, my friends, sometimes we're going to be able to construct a so-called inverse for a matrix. And when we can do that, which is what this next little talk is going to be about, we're going to mostly do this on Thursday, but just to kind of set the stage for that, if we can talk about an inverse of a matrix, then there actually will be some hope for this idea of sort of solving for x by dividing by the matrix. So how is this going to work? Let me just in the 1 minute I have left, I'm gonna write down a quick definition here to kind of set the stage for this. Okay? And right away, we're going to let A be an n by n matrix. You remember that handout that we started off the class with today with the square matrices? Well, that was pretty important, right? It turns out that this section doesn't even make sense if the matrix is not square. So like right here, this matrix A was 3 rows and 5 columns. It's not a square matrix, so nothing I'm talking about over here is going to be relevant over there. But in this case, if, this is a big if, but if there is an n by n matrix capital B with A times B equal to the identity matrix. Like guys, let's just remember for a second. You kind of remember the identity matrix is like multiplying by 1. It plays the same role in matrix land that the number 1 does, right? So just think about numbers for a second, you know, so if you had a number like 5 and you could multiply it by something to get 1, then those two numbers, the 5 and the 1/5, they're like inverses of each other. They kind of cancel each other out. That's literally what I want you to be thinking about. I do have to also require that B times A is the identity. Remember that matrix multiplication normally is not commutative, so we can't just assume that if A times B is the identity, then so is B times A. So if this is the case, I'll wrap up with this. We call B an inverse for capital A. And if A happens to have an inverse, not every matrix will, but if A happens to have an inverse, then we basically can use that in, I mean, I could basically do this, guys. I could multiply by that inverse on both sides of the equation. B times A kind of cancels out to the identity matrix and you solve for X. So you actually can make that work. But lots of questions here. How do we know if A has an inverse? If it does, how do we find it? Right? These are great questions, but you know, in my soap opera style of teaching, right? I used to watch soap operas when I was growing up. I know it's like the embarrassing little fun fact about myself. So it would always be kind of slow until the very end, and then there was always something that would like the music starts building and it gets very dramatic, and they find a way to hook you to come back for the next episode the next day or whatever. So I kind of thought, oh, well, that's maybe a good way to teach my classes and give people a reason to come back the next day and find out what is coming next. So on Thursday, I will talk much, much more about this very powerful idea of using an inverse of a matrix. Thank you so much, guys, for your attention today. I look forward to seeing you soon, either in office hours or in person. Hey.